All right, I'm Math 3 distance learners. We are starting our new unit today. Hopefully everybody had a great Thanksgiving break, but we're ready to close out this semester strong. We're finishing up with exponential equations. Now, what we have done and what you're going to see today's lesson in particular shouldn't be anything that you haven't seen before. I'm pretty sure that every single year, iMath 1, iMath 2, and then again this year, you've dealt with exponential graphs. And they're, for me, one of my favorite topics to teach because they have a lot of real-world application. But we're going to start with the basics today. So to get things going, well, let me go ahead and do my intro and then we'll get things started. All right, so to get things started today, we have these 4 sequences, and here's your task, okay? I want you to look at all 4 of these, and in your notes, you'll write them down, please. So you'll copy these down. I want you to find the pattern, and you can write out on your notes. Once you've written these out, each of them, you're going to find the pattern that you're seeing within this. And then this is something you would have done in iMath 1, I believe. You're going to describe it as being arithmetic or geometric. Now, we're going to define those in a minute, but again, this is a review. So, if you can't remember, that's fine. If you want to look it up on the internet, you can do that. What are the definitions for those? That's fine with me. However long you want to take doing this is okay with me, but I'm going to go ahead and pause it for you to get your answers. Okay, so you had a chance to answer these. Let's go ahead and get started. Now, this first one, hopefully you saw the pattern was plus 5, okay? Plus 5. We'll come back and decide if it's arithmetic or geometric in a second. Right here, this is divide by 2. Excuse me, not 2, 3. My division symbol, I don't really have one on here. Divide by 3. Each time there's division happening. Next, on this one, we are subtracting 4 each time, and then this bottom one here is times, we're multiplying by 3 instead of dividing by 3. So those are all the patterns here that we're seeing. Okay, so times 3, I can't get that to be small. Okay, so times 3, divided by 3, we have all the different operations occurring. So now we want to decide, we're going to write down 3 definitions, okay? First definition you're going to write down is sequence. So go ahead and write the word sequence for me. So a sequence is a list of objects, numbers or objects in a special order. So that's your definition. Go ahead and write that down and pause it if you need to. But again, this is not a new idea. This is something you learned in iMath 1. What we're particularly interested in is what an arithmetic or geometric sequence is. So the next definition that we're going to be looking at is an arithmetic sequence. Go ahead and write down the word arithmetic sequence. And then an arithmetic sequence, and here's our definition, is made by adding the same value each time. Okay, made by adding the same value each time. So that's our definition for it. Nothing new again. Then we have geometric, so I'm going to scroll down. Geometric sequence, so we'll write geometric sequences. It's our definition. Made by multiplying by the same value each time. So there's our key difference between those. Hopefully this isn't something new. Hopefully you learned it really well in your freshman year, but it doesn't hurt to go back over this. Underneath arithmetic sequence, go ahead and write this. The value added each time is called the common difference, okay? So even though difference makes us think of subtracting, sometimes you can subtract, and that's an arithmetic sequence. You're adding a negative number is kind of what that would be. But we always call it the common difference. So go ahead and write this down under arithmetic for me. We're going to write something underneath geometric. We have the common ratio. What we multiply by each time is called the common ratio. Okay, common ratio. So that's what we're going to be doing in this chapter. We're more focused in this chapter on geometric. Arithmetic, again, that's very freshman year. We're more interested in these geometric sequences this year, and we're gonna push the limits on these and really learn something cool and interesting with it. So let's go back here. So number one, is this arithmetic or geometric? Well, since we are adding each time, this is arithmetic. If I can spell it right, even though it's right above me. Arithmetic. Divide by 3. Well, addition was very easy, but division, usually when we're talking about, we know that that's not happening for arithmetic. We're not adding or subtracting something. We are multiplying. So when we say dividing, that's the same as multiplying by what? By 1/3, right? So if I'm multiplying something by 1/3, that is the same as dividing by 3. So really our common ratio is 1/3. And hopefully that makes sense when we say the word ratio, right? We should be thinking fractions. So there's always multiplication happening in these. We don't want to ever really call these division, okay? Even though you're seeing the pattern of division, call it multiplying and create a fraction that shows that. All right, so that's got to be geometric. What about this one? Subtract 4 each time. Well, that's arithmetic. And let's put it into a more additive form, because we said arithmetic sequences are made by adding the same value each time. So let's put it that way. Let's say adding -4, right? That's what we're doing. We're adding -4. That makes it arithmetic. Finally, we have this sequence here. We said it's times 3. Well, that's very easy to distinguish as geometric. And for my OCD people, I'll go back and capitalize this G here so that it doesn't bother you. So that's, again, this is should be more review to start us off today. Let's go ahead and talk delta math really quick, because this is going to be important for that. Let's pull this up, let it load here. So I haven't finished creating this just yet, but I know one of the problem types you have are going to be like this. Let me get you a new problem. So you're going to have a sequence. You have to determine, is it arithmetic or geometric? Here we have 5, 25, 125. Hopefully you're able to see that this is geometric. If you're having trouble determining the common ratio, we'll go ahead and say this is geometric. So it would have either a common difference or a common ratio. Here we have a common ratio because it's geometric. And we can see that it's times 5. Now, if you're having trouble seeing the actual pattern, you can take each of these numbers and divide them. So do the first number and divide it with the number before it. So I'll do 25 over 5. And then I'll repeat that with these, right? 125 over 25. And you'll notice that these are all equal to 5. So that tells us what our common ratio is equal to. So these shouldn't be too hard. Again, you had to do this in your freshman year. We're probably going to talk about this terminology A1, A2, A3. We may or may not. Actually, we're going to have to for series, but that's going to be the idea here with these. So on this one, it's times 5. Here we are. So let's look at this one, 64. Again, if I can't figure out the ratio, all I have to do is take, because on this one, it's obvious that we're not subtracting. So all I need to do is take the 16 divided by 64, which should be equal to 4 over 16, right? So these should all be, if I do this divided by this divided by this, it should give me the same ratio, which is actually going to be 1 over 4. And that's how you want to submit your answer into delta math. So we do this, it's geometric, the common ratio is 1 divided by 4. And that's going to get us the right answer. So this is should be a pretty soft start to what we're getting into here. Now let's talk about a little bit more about what we're most interested in for this chapter. We care more about geometric, okay? Because when we're looking at geometric sequences, they relate to a particular type of function that we are interested in. Okay? So let's go ahead and look at some examples. I'm going to use Delta Math on this again. I'm relying on Delta Math quite a bit to help me this year, obviously, for distance learners. So I want you to look at this. This is the next section in Delta Math that you're going to have. Okay? So I'm going to pause the video, and you have to pick what type of function this actually is. Okay? We have not a function, quadratic, linear, and exponential. And you'll have to do this on your Delta Math, but we're going to start with this example. So I'm going to pause, and you are going to pick the answer that you think it is. Okay, so you have picked an answer, and you should have picked linear. Let's talk about why. Because, and we've already been through a section like this, what we're usually doing to find this is we're finding these rows of differences, and we're looking for a common difference. So we see here that the common difference is 2. Okay? So that's a linear example. And in our solution here, it says, yeah, constant is at +2. It's a constant rate of change. That's linear. Let's get a new problem. All right, so we're going to try this one. We're going to try the same approach, but I'm going to let you take a moment to try to figure this out. So I'll pause, and you pick which one you think it is. Okay, so I don't know what this one is right off the bat. I'm looking, it looks like, actually, no, it's pretty obviously linear. You'll notice the change is +5, right? So let's just do linear. All right, so we're getting a lot of linears. This one's linear, that's +3. I'm going to skip it. Interesting. Okay, so let's look at this one. I'll pause it. You tell me what you think it is. Okay, so for me, I am thinking that this one's quadratic, just right off the bat, the way the pattern looks. What we're looking at is the y values, right? We don't really care about the x values. The x values they are what they are. They're the domain. We're interested in the range, what's happening here. This is the right column is the actual function. So let's look at the changes that happen in here. So we get +0. We got +2. We get +4. And then we get +6. So this means it's not linear for sure. There's no constant rate of change. But this was one of our first chapters. Remember, we kept finding the differences in the table. So we're going to go again. And what we notice is we're adding 2 every single time here. Okay? Adding 2 every single time. So this is an indicator that this is a quadratic. All right? And so, because the second row of differences is constant, so quadratic should be right. Let's see their explanation. Okay, so the rate of change is constant. The rate of change is not constant. It's +0, +2, +4. So the rate of change is constantly +2. So that's from this rate of change here. The change in the change there. Okay. We need to find one that looks exponential though. That's linear. That's also linear. There's a lot of linears in here. I don't like that. I want more exponentials. That's... What is this one? Is this one quadratic? 7, then 9, then 11. Yeah, it's quadratic. Is this one... Let me pause until I find one. Hold on, I'll skip ahead. Okay, so I have found an exponential. I was hoping for a little more drama in finding one and having you sort of see it, but this one's exponential. So let's talk about why. Look at the values here. If we found the differences, we would never get a common difference. So let me show this. This is 8. This is 16. This is 32. 64. And you'll notice, watch this, as we go this way, it's just going to repeat itself. And this is very characteristic of an exponential function, okay? This is very characteristic of that. So how can you notice this? Well, look at the actual pattern here. See the pattern in these numbers. When we go from each y value, it is doubling, right? Times 2. Times 2. Times 2. Yeah, it just keeps doing it. This is that indicator of a geometric sequence, correct? It's made by multiplying by the same value each time. We're doubling these values each time. The y values are doubling. That is the pattern. So that's the indicator of an exponential. So that's where we're tying together this idea of geometric sequence and exponentials. All right, and this connection should have been made before today. We're just going back through it. This is just our easy in to the topic. All right, and we're going to do the final skill for today. There will be another lesson this week over geometric ideas, and I misspelled this. I need you in your notes to draw a line, and let's write this up. Creating an exponential function from a geometric sequence. Okay, that's what we want to do. So I have this example here that we want to use, and we want to create the equation of the exponential function represented by this table. Okay, so for exponential functions, they're always going to be in this form: y equals a times b to the x. This is exponential. The reason it's called exponential is because the exponent is the variable. That's where it gets its name, exponential. Okay, so we need to keep that in mind. So let's talk about a. A is the initial amount or initial value. And you would have done growth and decay functions as a freshman and possibly last year, but this right here is going to be important to review for when we get into interest. So initial value. So in this case, what is a equal to? Okay, and let's go ahead and put in parentheses where x equals 0. This is the starting point for this. In a list of sequences, it would be, so for this one here, it'd be 10. That's the initial value, right? And then you're dividing by 3 each time. So we're going to talk about that. So let's go back to this. And then next, b is the common ratio. I really do miss my Moby pad. I talked to Miss Evans about getting me another one. So common ratio. Okay, so what is the common ratio? What's happening as we go from each one of these? We already know this is a geometric sequence here. We're looking at these y values. Well, what's happening? Well, this is times what? Well, that's times, should be times 4 each time. So times 4. Times 4. And that's a consistent pattern. So we have b is the common ratio, which is 4. A is the initial value where x equals 0. It's the y value. I'm going to say y at x equals 0. Well, that's 0.2, right? That's the initial value. So we start our equation y equals 0.2 times 4 to the x, and we're done. That's all we need to do. Now, obviously, this is a delta math problem, as you can see. I just wanted to put it on a slide for us. So I'm going to type that in, 0.2. I'm going to use parentheses here. We're going up by 4 each time, close them, exponent x. Submit the answer. I got it right. Okay. You notice they do their multiplicative rate is what they call it. This is just the common ratio. That's all we have here. And then this 0.2 is, they call it the y-intercept. This is our initial amount, right? I want to keep it in the terms of initial amount and common ratio or rate of change here. Or common ratio is better for us. Just so that we can get into our compound interest. But this is what you're going to be doing. I just want you to practice with these delta math problems, finding that rate of change. So some of you may say, well, how do I find the common ratio if I'm looking at something that looks so complicated as this? Well, all you need to do, got a calculator, just take take each of these and divide them, but you want to do the value before. So it's this one. I'm going to take this divided by this second one here. Okay, so we take that one first. So 0.01 divided by 0.02. There's our ratio. Let's repeat that with the next one here. I want to do it with this one, these two. So just to confirm, 0.005 divided by 0.01, 0.5. So we're halving these values each time. Here's our initial amount up here in blue. This is where we started. So when I'm looking at this, I'm just going to do 0.02, parentheses, 0.5, raise it to the x. That's all we have to do, and I just want you guys practicing that. And our next video is going to be all about these geometric series, but this is at least giving us a good refresher into what we learned over the past 2 years. I'm assuming these exponential equations and functions. Okay, so you only have 6 of those. There's 10 of these. 10 of these shouldn't be too difficult. Let me talk about one last item on here. Because there's examples where they're not functions, so not a function, and let's talk about that because I don't want you to be confused. Notice why this one's not a function. We're not going to really get into our definition of functions, but notice how the x values are repeated. If I put, this would be -3, if I put linear and I saw that, it would count it incorrect because it says 4 shows up twice as an input and has 2 different outputs. So that's just a little definition of function. We're not going to harp on that too much, but it will give it to you wrong if you don't have that. Our goal is to not put that like on a test or anything, but just be aware that if you see repeated x values, that means this is not a function, especially if they have different, if the repeated x values have different y values, then it's not a function. Okay? So we're going to stop the video there.